Welcome back to Learn as you explore, your go-to place for mBot2 tutorials. If you're excited to grab the mBot2 or any accessories, check out the links in the description. If you use the links, I may earn a commission at no extra cost to you. Alright guys, let's do a quick recap of our previous project where we programmed the robot to track the ball by moving forward and backward. Assuming our ball is in this location in the frame of the camera, let's first draw the X and Y axes on the image. As we saw in our previous video, Y goes from top to bottom and X goes from left to right. We want the ball to be centered vertically, so we'll set our target Y to the center coordinate as shown here. The smart camera then gives us the ball's Y coordinate, and we can now compute an error between the target Y and the ball Y coordinates. This error is computed as target Y minus the ball Y. Our goal is to reduce this error to 0, or at least close to 0. And the action we want to take is to move the robot in such a way that the error is reduced to 0, or at least close to 0. So we can command the wheel power as a function of this error Y value that we've computed. So in this case, since target Y has a lower value than ball Y, again, remember that Y goes from top to bottom, which means values increase from 0 all the way down. So target Y has a lower value than ball Y. Because of this, error Y is negative, and with the negative error Y, the robot will drive backward because the wheel power is a function of the error Y value. And the robot will keep driving backward until the error is close to 0. When the error is exactly 0, the wheel power also becomes 0 and the robot stops driving. Now let's take a different case. In this case, target Y has a greater value than ball Y, and so error, which is target minus ball, is going to give us a positive value, and when error is positive, the robot drives forward because the wheel power is a function of the error Y value. As the robot drives forward, the ball moves backward in the image, and that causes ball Y to get closer and closer to target Y, making the error 0 eventually. So from this, our main takeaway here is that error Y takes care of centering the ball vertically in the image. Now let's move on to our project for today, which is tracking the ball in all directions, meaning forward and backward, and also left and right. So here's the main question. What if we want the ball to be centered in the image, not just vertically, but also horizontally? To do that, let's set our target X value to be the horizontal center of the image. We can then get the ball's X coordinates from the smart camera. And the difference between the two is error X. Error X is computed as target X minus ball X. Once again, our goal is to reduce error X to 0. And the action that the robot can take here is to turn either left or right. Similar to the previous case, we'll compute a power as a function of the error X value that we computed here. We'll call this the turn power. Now in this case, target X has a lower value than ball X, and so the error value is going to be negative. So let's think about what we want the robot to do in this case. Because the ball is to the right of the target X coordinate, we want the robot to turn right. And when the robot turns right, the ball is going to move left in the frame of the camera. So just remember that the ball is not physically moving, but because the robot turns right, the field of view of the camera is shifting to the right, and hence the ball moves to the left in the frame of the camera. And if the ball moves left, the error X value keeps reducing until ball X and target X are on the same line and error X becomes 0. So in this case, we want the robot to turn right. If the robot were to turn left, error X value will keep increasing, and that's not what we want. Now that we've established that turn power should be a function of error X, and that in this scenario, error X is negative, and we want the robot to turn right, we can then think about the individual wheels now. If we want the robot to turn right, the left wheel should move forward and the right wheel should move backward. That causes an in-place right turn. Since in this case error x is negative, turn power is also going to be negative, and since we want the left wheel to move forward, left wheel power becomes a function of negative turn power. Now let's think about the right wheel power. We know that error x is negative, so turn power is also negative. We want the right wheel to move backward, so we can set right wheel power as a function of positive turn power, but because turn power itself is negative, right wheel power becomes negative, and hence the right wheel moves backward, while the left wheel moves forward, causing the robot to turn right. So let's lay this out step by step. In this case, error x is negative, so turn power is negative. Left wheel goes forward, right wheel goes backward. The robot turns right, which means that the ball would move left in the frame of the camera. And this causes our error x to reduce until it is close to 0. Now we have a way to center the ball vertically using the error y term and center the ball horizontally using the error x term. But how can we combine these two centering algorithms to track the ball in all directions? We know that vertical centering can be achieved with the wheel power that is a function of error y. We will rename this wheel power to forward power because now we're going to have two powers. We're going to have a forward power and a turn power. So vertical centering action can be achieved with a forward power as a function of error y. We know that the horizontal centering action can be achieved with a turn power, which is a function of error x. And left wheel power is a function of negative turn power, and right wheel power is a function of positive turn power. To combine the two centering actions, we can simply sum up the forward power and the turn power. For the left wheel power, since it is a function of negative turn power, we will subtract turn power from forward power. And for right wheel power, since it's a function of positive turn power, we will add turn power to forward power. And this is the core logic in the algorithm that we will use to perform all direction tracking of the ball. Now, one final thing to note is we need to figure out what the values of target X and target Y are. We know from the Google search that we did previously that the Pixie Cam 2 color connected components resolution is 316 by 208 pixels. Given that we know this, let's find the center X coordinates, which is simply 316, the width of the frame, and divide by 2. So that's 158. Similarly, we'll get the center Y coordinate as 208, which is the height of the frame, and divide that by 2 to get 104. Since we want to track the horizontal and vertical centers, we will note down these values of target X as 158 and target Y as 104, and we will use this in our program. This summary slide contains everything that we will use in our program, and I will also add this as a pop-up on the screen while we build our program. Now let's head to mBlock and build our program, starting from the program we had in our previous tutorial. If you're a passionate teacher, check out the educator packs I've put together, linked in the description. Open up the program from the previous tutorial and save it as a new program so we can build on it for our current project. I'm going to call this all directions ball tracking and say OK. Alright, let's create some variables. We have the center Y coordinate, which is our target Y value. We now need a target X value as well, which we'll call center X coordinate. Go to variables, say make a variable, and call it center X coordinate. Say OK. We can then set the center X coordinate to the value 158. We have a scale factor, but that's only based on the Y coordinate value. So let's rename this to scale factor Y, and we'll create another scale factor for the X term. So go to variables, right click on scale factor and say rename variable. Let's call the scale factor Y. And finally, we'll make a scale factor X variable and click OK. We will also set the scale factor X variable next. And we want to set this to center X coordinate divided by max power percentage, similar to the Y case. So right click on this block, make sure to right click near the division block so that the entire thing gets copied, and click duplicate and drop it into the scale factor X. Now we don't want the center Y coordinate here, so delete that, and we'll bring in the center X coordinate instead. Drag that into your first operand, and now you have your scale factor X being computed correctly. We need another variable to track the ball X coordinate, similar to the ball Y coordinate. So we'll go to variables, create another variable, call it ball X coordinate, and click OK. We'll set the ball X coordinate here, and we want to set this value to the smart camera's detected X coordinate. So right click this, duplicate, drop it into the ball X coordinate set block, and change the Y coordinate value here to X coordinate. We then have a condition here checking if the ball is within the frame of the camera. When we were tracking only the ball Y coordinate, it was good enough to check ball Y coordinate greater than 0 to make sure that the ball is within the frame of the camera. But now that we're also going to track the X coordinate, we need to check if either the ball Y coordinate is greater than 0 or if the ball X coordinate is greater than 0. Since we need an OR operation, go to Operators, drag the OR block. You can then drag the ball Y coordinate greater than 0 condition and drop it into the second operand, duplicate it, drop it into the first operand, and finally we can replace this with ball X coordinate by going to Variables and dragging the ball X coordinate into its place. We can get rid of this extra ball Y coordinate. And finally, we can drag this and drop it into our if condition. If you're following along, you're doing great so far. Now, instead of calling this wheel power, we'll rename it to forward power, just like we did in our slides. To do that, go to the variables category and right click the wheel power variable and say rename variable, and we'll call it forward power instead. Say OK, and all your instances should be replaced with forward power instead of wheel power. Now, from our slides, we know that we need to compute turn power as a function of error X. So let's create yet another variable. We'll call it turn power this time and say OK. Now we need to set this turn power, so drag the set block right below the forward power block and set the turn power. The turn power's value is going to be similar to the forward power, only instead of Y coordinate values, we're going to be using X coordinate values instead. This makes sense because center Y coordinate minus ball Y coordinate is essentially error Y. If we replace these with X coordinate values, that becomes error X, where it's center X coordinate minus ball X coordinate. And we divide by the scale factor X this time to convert the pixel coordinate values from the image into wheel power values. So right click this block, once again, do it near the division operator so you can duplicate the entire block, and click duplicate and then insert it into turn power. Now we'll replace these Y coordinate variables one by one with their corresponding X variable counterparts. So for the center Y coordinate, we want to replace this with center X coordinate instead. So go to variables and use the center X coordinate here. Instead of ball Y coordinate, we want ball X coordinate. Once again, use the ball X coordinate variable from variables. Finally, scale factor Y needs to be replaced with scale factor X, which we can also get from the same block category. Now that we have the turn power computed, let's then compute the left wheel power and right wheel power. We'll need two more variables, one for left power and another for right power. So I'm going to create them now. Also make the right power variable, and let's set the left power and right power values here. For the left power, we want to set it to forward power minus turn power, if you remember from the slides. So let's get a subtraction block, and the first operand is going to be forward power, which I'll duplicate from here, and the second operand is going to be turn power, which I can get from variables. Finally, we can also set the right wheel power by going to variables, drag another set block, change this to right power, and this time we want to set it to forward power plus turn power. To do that, get an addition block from operators, and you can duplicate the forward power from here and the turn power from here as well. Alright, now that we have this, we can now set our encoder motor power values. So the first operand here is the left wheel power, which we call the left power in our variables. So use that to replace this one. And you can also get rid of this extra forward power. Similarly, for the right wheel, get rid of this extra forward power and use the right power variable instead. Remember to keep this -1 multiplication here, because when the right wheel is commanded a forward power, it moves backwards, and when it is commanded a negative power, it moves forward. So to invert that, we have this -1 right here. Now one last thing just to clean up is we were printing the forward power value here, but we don't need that anymore because that was for debugging purposes, and printing just the forward power does not really make sense. If you really want to see the power, try this yourself and print both the left power and right power, maybe separated by a comma, so you can see the individual wheel powers being commanded. But I'm not going to do that for this project, so I'm getting rid of that. And you know what? That is all the changes that we need. It wasn't that complicated if you really think about it. It's just that we needed to come up with the horizontal centering algorithm similar to the vertical centering algorithm, and combining those two together by either doing forward power minus turn power or forward power plus turn power, depending on the wheel, was the crucial part. Once you have that, pretty much everything else is straightforward, and you can easily come up with this program. I hope you had fun building this program. Let's go ahead and test it out on our robot now. Before that, click Save to save all your work. Make sure that the robot is connected to your computer and click Connect. Click Connect again and click Upload Code and wait for the program to be uploaded. Once it's uploaded, you're ready to go and test it out on the robot. Here are some of my other videos that you may find helpful. Happy programming, and I'll see you in the next one.